Can you see my screen now?
Yes.
Good, good. Okay. Good morning or good afternoon or good night, depending where you are at in the world. From me, I'm Luka Vucinic, and I am lecturer, as Sofie introduced, at Glasgow Caledonian University, based in the campus in central London. And first of all, many thanks to Sofie and Amaël and TRAQUA for organizing this webinar and for invitation to talk a little bit about tracing techniques that are not so common in modern times, but hopefully are coming back again. And thanks to Sofie for allowing me to be a bit creative, which is what I like to do with my title, and incorporating a bit of some of my other passions, such as this kind of books and films, such as The Lord of the Ring. So I created over there a little bit of meme style image that we shared on social media, which people kind of liked it. So it's a good approach. The talk will be serious. It's not going to be unserious, but it is fun to combine these things. So as you all know, before we start with the main part of the talk, we need put some kind of foundations, and many of you will be already aware about groundwater tracing, but nevertheless, these are extremely important in various disciplines, but I will be mostly talking about hydrogeology, because that's what I am, primarily a hydrogeologist. And we use a range of tracers, usually artificial ones, to conduct these kind of studies. But we also use some natural tracers as well throughout the years. At least we tend to use them to trace groundwater flow and in different hydrological and hydrogeological environments. And also these kind of techniques and approaches are of great value across many other applications that are not necessarily linked to hydrogeology. And I may mention over there just some of these tracers. They can be inorganic ions, radionuclides, fluorescent dyes that are most commonly used, but also microspheres that can be fluorescent, that can be dyed with fluorescent color and be fluorescent, various types of microorganisms and viruses, even natural sediments, and more. So you can see on the right side couple of images. These are mostly commonly used fluorescent dyes, rhodamine and uranin, and the photo I took from the website of Geological Survey of Ireland, where Ireland is a place where I spent most of the time in the last decade or so, a bit also in Northern Ireland, and I used their photos. I could use some of mine as well, but I just wanted to get an opportunity really to thank them for a lot of for a collaboration, for some funding that they have been providing over the years, access to some of their equipment, etc. So it was a good opportunity just to thank them and all the wonderful people who are working there, especially in the groundwater section. In terms of artificial tracer tests, we are doing them mostly in the context of harsh hydrogeology to establish connections between some kind of swallow hole or ponor, as we like to call it in back home, where I'm originally at, Montenegro, which is very country with a lot of karst, just like Ireland, a bit more even. So it's not surprised that I'm interested in karst hydrogeology. So the connection between some ponor, swallow hole, and a discrete outflow point, which will be usually a natural spring. We also use artificial tracer tests to estimate groundwater transit times, to assess hydrogeologic behavior of karst waddle zone. This is something that Amaël did years ago, and he published a couple of papers related to this, which are fantastic. To investigate conduit parameters, as well as transportation characteristics of potential contaminants, which is kind of what I'm going to be touching on today. So there wouldn't be Tolkien, Lord of the Rings type of theme if I didn't put a little bit of flavor of that in my presentation. So I generated this image using AI on the left side, and this is what AI thinks Bulembu should look like in a karst cave. So you will see. I don't know how accurate it is. Obviously, in the movies, hobbits do not wear boots, but it is what it is. And on the right side, you see some photos where I use dyes, in this case rhodamine, to trace some kind of connection and understand a bit properties between certain points in the west of Ireland. And obviously the title, why not just dyes, Gandalf? Wouldn't be enough on their own? And that's the kind of question why we need yeast if we have dyes that are working very well. Well, again, another AI-generated image and a little bit of text in italic that what AI thinks how I should, spread this message in a Tolkien-like style. Well, dyes do not really behave as microbes, as pathogens, microbial pathogens, and particles in the karst subsurface, in the karst aquifers. So many studies actually reported faster travel times and lower recovery rates for particles in comparison to solute tracers, such as fluorescent dyes. So we obviously dyes can tell us a lot of things, but when we want to understand the transport of pathogens, pathogenic microorganisms through the subsurface because of the primarily public health reasons, then dyes have really limited value in that kind of context. So that's the key problem, and this is the problem that we are trying to solve. So no tracer is perfect, and since we kind of understand that particles and microbes will travel differently through the karst aquifer systems, we are trying to approach to this kind of problem in various ways. So this is a special concern from the public health perspective. In karst, we know they are exceptionally vulnerable to contamination because of the nature of the karst. And even in more recent times, which is something that not all people are necessarily aware of, is that we have groundwater contamination, bacterial contamination, such as contamination with E. coli and other pathogenic microorganisms, primarily of fecal origin, even in so-called developed world, not just in the developing world. So in maybe 24, 25 years ago in Walkerton in Ontario, Canada, there has been an incident that has been widely publicized and known in a highly fractured environment. So that kind of gained a bit of publicity, I would say, even in the West, so-called West. So I added on the right side, a movie film, Betrayed, that has been kind of inspired by these kind of events. So it's not really a documentary; it's kind of fictional story that has been inspired by this incident and some others across the world. So that's another way how we can spread our awareness about this kind of hydrogeological problems. And I suppose this is why I also love films so much. They are very good for communicating these kind of problems that might be difficult to understand to general public. So the question is why particles and microbes might travel faster in the karst subsurface, in the karst groundwater, compared to dyes and other solute tracers, and why they have lower recovery rates. Well, there are a couple of explanations, but the most commonly accepted explanation is pore and size exclusion processes, because microorganisms and particles cannot enter smaller pores or the pore space closer to the walls, such as the walls of the conduits. where usually lower flow velocities occur. That has been very well explained in the paper published by Nadine Gopper and Nico Goldschneider, two very highly famous names in Karst hydrogeology and especially in tracer tests. So as a result, the absolute tracer tests are considered to be of limited value in predicting the movement of microorganisms and other microbial pathogens in karst aquifer systems. And while they have been historically used, different microbial tracers, this is still not a standard method used in karst hydrogeology. And I don't think that these kind of methods will be ever be used again as a standard. They might be as a supplement to standard methods, but I think what we accomplished with dyes in terms of detectability and the ease how we can perform these tests, I don't think that's going to be that's going to be hard to match, really. So we have a challenge, and the challenge is to supplement our dye tracing tests and trace microbial movement at the same time through the subsurface. But to do so, we need to find widely applicable, inexpensive, and readily available tracers that will accurately mimic microbial properties and behavior during that transport into the karst subsurface or other groundwater subsurface environments, and which will also pose no potential threats to the environment and especially public health. So that's a bit tricky. So what best can mimic the microbial properties than the microbes themselves? However, even those that we used previously, historically, as a tracer, such as Serratia marcinens bacteria, which is kind of pinkish dyed, naturally pinkish colored bacteria. We can't use them anymore because they are classified as pathogens now. Historically, not necessarily they were classified as pathogens, but now they are. And if you see those kind of, I added a few images showing how they look like, the colonies on one side, and over there you will see in the toilets. Some of you might notice them in the sinks or in the toilets, in your bathrooms, maybe under at some places in the shower. They usually tend to get there in a very damp environment. They get to grow there. If there are any residues of soap or some kind of fat or anything that's really phosphorus that contains a bit of phosphorus. So hopefully you haven't seen them in your toilets, but that's basically how they look like. Another aspect of this challenge that we are trying to solve is that these artificial tracers that will accurately mimic these microbial transport in the subsurface and properties should be easily differentiable from the microbes and particles already present in the groundwater, and should be easily detected at very low concentrations with reasonable analytical costs. And also that method needs to be not complicated to perform and not highly time consuming. So I added some historical methods and approaches that have been used to detect these kind of tracers and enumerate them. So obviously looking and counting under the microscope is not really, it's complicated and it's very time consuming. So as use of digital colony counters, that I just picked a photo of a random one. You can buy these even at Amazon for like £200, €200, £200, something like that. So that's kind of what we are trying to accomplish. And this is not a novel idea to use yeast or to use this kind of microbial tracers. In fact, if you look first the figure on the right side, you will see basically you will see what has been historically used from the end of 19th century and throughout the 20th century. This is from the paper that has been published by the end of the last century, so it's not most up to date. There is a review paper that is more up to date than this one, but I just wanted to show you basically when yeast we first kind of see in the scientific literature. So it was more than 100 years ago, and then spores in the 1950s, and then yeasts again in the 70s, and since then we kind of forgot about them. And we forgot about them because of the problems associated with recovery of those tracers, detecting them at low concentrations. And then you see from another paper from the, from 𝗦𝗲𝗻𝗲 from 1978, when one of the last publications where yeast has been published appeared. It's not the last, but it's among the last ones. And you will see this is actually a laboratory study, and you will see I just circled in red 2 numbers to count. So they managed to count them. It took them a lot of time and took them a lot of effort, but in the end, it was not efficient. And that's why somehow yeast dropped out of our sight and become slowly forgotten as a tracer that we can use for these kind of Karst hydrogeology applications and maybe some other. So the new review paper that I mentioned is by Danish, and it was published in 2021. So if you're looking for more up-to-date information about all the types of tracers that people used in the past or you might use, that's the really good publication to go to. And this is from where I kind of saw and realized that these yeast and coloring spores with fluorescent dyes is playing only a minor or no role in modern Karst hydrogeology because of the issues that I've mentioned, to the detection, identification of those traces, labor-intensive and time-consuming aspects of the work. So yeast become forgotten, and we know it's good. So why yeast? If you don't know why it's good, it's not naturally present in groundwater in any significant concentration, should not be. There might be some small concentrations of yeast because, especially in the agricultural area, after all, they're giving them to domestic animals such as horses. They're feeding, improving nutrition of horses with those, and that's how we can buy them cheaply as well. They're not associated with any known human health or environmental concerns. The types of yeast that we can use. There are many types of yeast. Some yeasts are pathogenic, but we are not using those. So I just want to clarify that yeast is it's a large of family of types of yeasts, and you don't really need to look into those that are pathogenic. You can simply just look on the other side, and you have plenty of those who are perfectly safe. It's readily available and inexpensive. It's round to ovoid in shape, which is great because it resembles the shape of most pathogenic microorganisms that are interested to us from the fecal pollution point of view. And they can vary you can find them in different sizes. So that means that they can also cover various sizes of most known pathogenic organisms. So they can vary between 1 to 40 microns. So that's also great. So these are kind of the reason why yeast is, in my opinion, so important for this kind of studies. Now, we talked about the problems associated with historical detection of those tracers, but when those tracers have been done in the past, these new modern technologies were not either yet there, or they were not emerging as tools that we can use in environmental microbiology or hydrogeology, etc. So one of those is actually flow cytometry that has been present and has been used for environmental purposes for a while now, and it's there with us since, I believe, 50s or 60s, when it really kicked on in terms of their applications in biomedicine and those areas. And here I just showed one that I used, which you absolutely do not need to use. There are so many flow cytometers out there on the market, and you can pretty much analyze and get your tracers and your samples analyzed with any of those equally. And on the bottom side, you can see portable particle counter. And again, there are so many of them, and they have also some kind of additional gadgets that you can use inside. So they are perfect. This particular one I use because it's great to be used in situ. And it was being used by some others as well in the recent years, also for tracer tests with different tracers, such as sediments, for example. But what was not available at the time when I conducted my tracer tests with yeast, that I'm going to talk about today a little bit later on, was the addition on the right side, which is automation add-on for flow cytometry. In this case, it's specifically built for this type of flow cytometer. And this is built by a company from Switzerland. It's a spin-off company from IMWA, and they also have their own fully automatized flow cytometer that has everything inside. So what is the difference? Why we need this automation? Well, in order to analyze tracers, analyze cells, anything cell-like with flow cytometry, including yeast in this case as a tracer, we need to use dyes. So we need to kind of prepare our samples, dye them with either one or two dyes. I'm not going to go into details about that, but you really need one dye for tracer tests in the context that I use. But there are additional opportunities with two dyes method, so you can actually potentially, if you choose some, for example, other types of tracers that you want to simulate, for example, E. coli, that has been deactivated, so it's not pathogenic, which has been done by a colleague in the United States in the recent years as well, then maybe if you kind of mark those E. coli and inject them, then you will be able to, with the two dye method, even estimate their die-off rates while they're traveling through the Karst aquifer system. So a lot of really exciting new opportunities in this kind of context. And particle counter is great to be carried around. It doesn't need staining. So unlike flow cytometry that requires you to do some kind of lab-based, which is quite not expensive, quite cheap and easy to do. So it's not complicated. You don't need that with portable particle counter. So there are pros and cons, but some other aspects of particle counter might be less favorable. So we don't do these kind of things in the lab. The colleagues, spin-off company from Switzerland, created this kind of automation dye add-ons that can do that for you. So it can be brought on site. You can install your flow cytometer with this add-on, and you don't need to do dyeing. You don't need to use your hand, take your samples in the lab. It will be done automatically. So that just shows how this kind of, I would say, this kind of area is getting some kind of rapid interest and some kind of exciting developments, I would say, as well. So it's becoming an important portable particle counters are becoming very important tool due to their mobility, ease of analysis, and ability to detect particle tracers in extremely low levels. And flow cytometry is more sensitive, but a bit more complex if we need to do some kind of preparation for the analysis in the lab. But it's showing a bit more promises, especially if our next step is to try to not just to trace microbial movement and understand that in terms of travel times and how it behaves in the subsurface, but also to understand maybe die-off rates in the subsurface in different conditions due to different temperatures, presence of nutrients, etc. So on the right side is one of the papers, recent papers that are looking into this. This has been published this year, so this is just for you to look at as a reference if you're interested to find out more about it. This is a graphical abstract, and again, as you can see, another film reference, Back to the Future, and DeLorean. It's hidden over there in the graphical abstract as well in front of the house. So obviously, I like these kind of things, and we used combination of yeast with rhodamine and uranine dyes on two locations, on two test sites. And you can see in the graphical abstract that we use some field fluorometers as well, the flow cytometer that I mentioned, particle counter system, but also we also collect in the test too. We collected samples with ISCO automatic samplers and analyzed them with fluorescent spectrophotometer. So a range of different approaches to test basically what's better and to kind of understand better the possibilities with flow cytometry versus particle counter systems. So these are the test sites, two sites in the west of Ireland, one in the county Galway and the other in county Limerick. The first one is in a very large Karst system. The swallow hole is known as a Castletown sink, and the linear distance to the spring, Kiltartan spring, is a little bit more than 1,000 meters. And for the second one, there's a swallow hole at the edge of one of the edges of the Lough Gur Lake, and the linear distance is 1,788 meters until the Creamery Spring. The other spring next to Creamery Spring, Field Spring, is usually dry during the low flow conditions. So when these tests were carried out, so it was not monitored as a part of the study because it was completely dry. At this slide, you can basically see what we did. Couple of photos showing mixing yeast with the water from the same catchment. That is very important because you don't want to introduce any other microbes that are not already naturally present in the tracer, and you don't really want to use distilled water because first of all you will need a lot of it to depending on the quantity of yeast that you need to kind of mix, and also it's not good for the yeast itself. You need to have some more favorable water than that. So mixing yeast with the water from the same catchment would be what I would personally suggest. And you will see tracer injections and also injection of rhodamine dye and uranine dye in the case of the second tracer test. So in terms of the results, first of all, we injected on the first site 12 kilograms of yeast and 7 liters of 20% solution of rhodamine WT dye. It was conducted in early September 2018 during stable low flow conditions, so there was no rain prior or during the test. And you can see from the results from the graph, quite quick test due to the rapid flow. And on the graph with A, you will see flow cytometric total cell count measurement. So we are measuring all cells present. On B and C, you will see different sizes of particles picked up by portable particle counter, and D is showing you rhodamine concentration change. So in this case, because it was so quick, it happened what we really expected. Both tracers appeared at the same time, reached their peak concentration at the same time, and were last detected at the same time, so they were really synchronized. So they underwent the same transport processes within the turbulent flow conditions. So there were no changes. So obviously, low flow conditions, no rainfall, very large system with a large conduits and high flow velocities resulted that in low conditions you will not have that kind of effect that I was explaining why we have different travel times. So this is, we observe the same excuse me, the same travel time on this route. Obviously you see that the breakthrough curve has a regular shape with a single peak and a very short tail. Again, something that's very expected. No precipitation occurred during this tracer test or 4 days before, and even that was happening 4 days was light rain, so it was not, there was no effective discharge really. There were also no noticeable differences in the shapes of the breakthrough curve in terms of between flow cytometry and portable particle counter, so both of them performed exceptionally well as well. Yeast cells across all monitor sizes. We injected sizes from 1 to 10 microns. That kind of ranges of yeast also followed the breakthrough curve almost identically. So also this kind of different yeast sizes behaved in those conditions identically. So both backup of modern approaches easily detected these tracers in this scenario. In case of tracer test 2 was conducted a bit later in the end of October and the beginning of November. However, this was still low flow conditions during a prolonged drought in Ireland during that year. And this is much smaller system, so we wanted to do something different rather than in a large system and putting very low quantities, which we did in the tracer test 1. We kind of injected a lot of it to see whether that will cause any problems in terms of detection, interpretation, etc. So we tried to kind of two extremes really with this approach. And then again, you see A, B, C, and D. There has been some rain throughout this test, so we include precipitation data, and in comparison to the previous tests, we used urine here as well. So we had here different outcome. The breakthrough of yeast occurred before the conservative solid tracer, and this has been confirmed using both flow cytometry, measuring total cell counts, that's what TCC means, and particle counter measurements. We detected multiple peaks, which is not unusual, especially at the conditions that we were encountering and considering the complex geology. So these kind of breakthrough curves can be explained in different ways, either individual flow paths with different flow velocities and dispersivities which converge close to the Karst spring, or another explanation can be remobilization of temporarily trapped tracers in some part of the conduit system near the spring. And then because we had some rainfall, you will see maybe these kind of rainfall pulses kind of pushed and remobilized several times these tracers. Remobilization that do not necessarily need to be from near the spring, could be also from other different parts of the aquifer system. So maybe there are many conduits that went in a different direction, although I find this possibility less likely than the previous one, but could be likely as well. And we can also consider subsurface storage of tracers that has been remobilized in some kind of low velocity zone of a trunk conduit, or in fractures, or in sediment, or in discrete voids in the rock matrix, etc. So there are different observations, and Karst is very complex. So we need to think whenever we conduct these kind of tracers. Maybe we have an outcome in mind, but something completely different happens, and then we need to think and really try to understand what happened there. Another potential explanation might be that the Karst network acts as a form of a siphon at this location, which has been explained almost 34 years ago by Bonacci and 𝗦𝗲𝗲, Croatian scientists, and that kind of siphon, that's kind of interesting story, but I'm afraid I don't have time to cover it today. So this kind of complicated geology at this site where we have volcanic rocks underlying limestone, and then also bands of low permeability clays that are intersecting some limestone formations, could also provide hydraulic constraints to support this kind of hypothesis of siphon on the route between the swallow hole at the edge of the lake and the spring. You will also be able to observe on the figure some differences in breakthrough curve between the different tracers and between different techniques that we use to collect the data to recover information from the tracers, but that's because of the differences in sampling and data acquisition frequencies, not really because of anything else. And this test also revealed to us clear differences between, in terms of transport and behavior, between the yeast and conservative solar tracer, in this case, uranine dye, between those locations. So to try to kind of wrap up what kind of main messages I would like to leave you with is that really we can use yeast again as an effective artificial tracer by using modern flow cytometry and particle counter technologies. Despite the fact that flow cytometry is a more sensitive technique that can detect cells, in this case yeast, in extremely high resolution, while the portable particle counter cannot differentiate between cells and debris, which flow cytometry can. No significant advantages we observe and on the basis of these two tests. However, it's worth mentioning that, which I already kind of mentioned briefly, is that flow cytometry has some kind of other opportunities waiting to be further explored. It's also important to know that flow cytometries can be deployed on site using additional equipment that I showed you in a couple of slides before, which was developed in the recent years. So when we conducted this tracer test, we brought those samples back to the lab and analyzed them. Now you can do them in situ as well. These technological advances in terms of flow cytometry and making these portable particle counter technologies better and better in terms of resolution as well, smaller and smaller, and easier to carry around, are making them attractive for these kind of applications as well. And sorry, on the previous, you can see a picture of me setting up one particle counter in the west of Ireland. And on the picture, on the photo here, you can see my colleague, Professor David O'Connell, being frustrated because of some of the equipment we tend to use for this kind of purposes. Not always things work as planned. Sometimes the equipment can fail you. It's technology after all, and then you have to have some kind of contingency plans in place. So both of these technologies should provide new lease of life for yeast as a Karst groundwater tracer in the future. It's not going to become conservative. It's going to be like a dyes, but it can be used more and more, and at least I believe so. However, if you are looking to use this kind of particular tracers, such as dyes, such as yeast, in different environmental and hydrological conditions, or like maybe you don't want to use it in Karst, then you will have other challenges. And then if you have even more challenging Karst, things can become a bit difficult in numerous ways. And different hydrological conditions, high flow conditions with a lot of rainfall events that are bringing different types of microbes from the nearby agricultural fields or whatever. They can also maybe provide you some peaks that are not necessarily your tracer peaks. So that's why we can't drop fluorescent dyes, even though that we want to use yeast. We need them in this kind of cases, not just for comparison, but also to cover different detectability chances, and also to confirm in some cases if it's high flow conditions with a lot of rainfall events, and we might not be sure whether our portable particle counter picked up the pollution or our tracer, then we can always have dye to help us to confirm that. So dyes will stay with us until the end of time. That's what I think. So, and with that, I will finish my presentation. Hopefully, it was not too long. Hopefully, it was interesting. And obviously, to conclude, that in the same way as I started, I just included one of the photos of me with a figure of Gollum. Thank you very much, and I'll be happy to answer some of your questions if you have some.
Hi, Luka. Thank you very much. I've read your paper just when it came out. I thought it was very interesting, so I urge you all to go and check it out.
Thank you.
There is already one question from Philip Alexei. He asks, thank you, Luka, for your work. Could you tell the time shift between first detection of yeast and uranin in two tests, in the second test, I guess?
Sorry.
And also between peak maximums.
Yeah. So I'm just going to go back. So the detection for the first one was very quick. The difference was between an hour or so. So there, even with this kind of relatively short travel distances, well, not really that short, but short enough, you can see the difference was considerable. In the longer distances, which would be more interesting, I assume those differences would be larger, and that's where we want to apply this kind of technique to cover different follicles near maybe some septic tanks or some farms, and understand if the pollution occurs between that follicle and our spring that we are maybe considering it for the public water supply, then or maybe can be well, then we really want to know if we use dye, it might underestimate the speed of the microbial tracers, and that can cause a problem. So in this case, it was really we kind of expected in both of these two kind of scenarios to happen. We didn't expect so many peaks in the tracer test too, but we expected the differences between the time. So the goal was to conduct relatively simple tests to test whether it's possible to use it and to understand a bit more opportunities, and also maybe some issues or challenges that we are going to be facing. So this is why we took those. So they should not be taken as representative as the work that should be done. It's just the work that showcases what might be done.
Okay, thank you. I hope this answered your question, Philip. I have a question myself. You used rhodamine in one test and fluorescein in the second one. Why did you choose different fluorescent traces for both tests?
Well, we wanted to check those two. In literature, they might be behaving slightly different, but to be honest, in the first test, we had plenty of rhodamine as well, so we wanted to use it, and there was no constraints in terms of legislation with rhodamine, and also we use it in a very large system, so the concentrations of rhodamine WT when injected were already low, and with the dilution effect, those concentrations were too low to pose any kind of problems to any kind of species that might be living in the subsurface. So it was not considered as dangerous. And in Ireland, I know that you did a lot of work on different dye tracers and pros and cons and different legislation contexts. Yeah, in Ireland at least, there's no problems associated with rhodamine WT, but in some places they are, especially with some kind of concentrations that are a bit higher.
Thank you, Luka. I think we can go. Oh, there's one more question. I'm sorry. From Tom Thompson, as a cave explorer, my main interest is improving connections. Does yeast provide an advantage over fluorescent dye?
No, dye would be, if you want to prove connections, dye is the way to go, the way to go. This is basically understanding the travel times of the microbes from the public health and human health perspective, from drinking water supplies, in the context of drinking water supplies, so we can get better idea, better information that we can feed later on to our models, or to provide us with understanding of protection zones, inner and outer protection zones of springs or wells and other public supplies. So this is purely for that kind of context. For any kind of proving connections, I would still go with dye. It's no-brainer, easy to do. The dyes can be detected in very low concentrations, so no doubts there.
Okay, thank you. Are there any other questions? Otherwise, we will move to one last question from Neda Devic. How much costs a flow cytometry?
They can cost from 20. There are some very small portable ones that you can buy for 1,000, 2,000, which are not very good. I can't comment how good they are for these kind of applications because you can't use them continuously. You just kind of put them in the water and kind of or introduce a bit of sample and then they kind of measure. So those are kind of cheap, but these ones like Akuri that are in the cheapest range of those more powerful ones, those would be between 20 and 30,000 euros, I think, depending also on what other kind of gadgets you want to buy and add on. So it can be up to 50,000 euros with all those add-ons.
Okay, thank you. One last questions, and then we will move on to the second presentation. So there's a question from Elena Bikova. So when we use fluorescent dyes, sometimes we have these traps that you can use with sorbent, like activated carbon bags, I assume that she's referring to. It allows to get results without direct observation. Is it possible to use some type of traps like that also for yeast?
Not really, because we are talking about microbes and it's really difficult to do so. The best way would be, automatic samplers. I'm not aware that you can trap them with anything. Possibly if those kind of, maybe some nets that will be trapping them, but then you're going into the more laborious aspect of work, and then you will need to analyze them more potentially with maybe we need to dye them as in the old times and then look them under the microscope. So yeah, I wouldn't really suggest trying that, considering that it's very easy to at least hire automatic samplers and analyze it.
Okay, there's let's do one more question and then we go. So thank you. From a question from Milan Petrovic. Thank you for the intriguing lecture. I'm interested. What is the least invasive and dangerous tracer for the environment?
That's hard to say. Anything that it's not hazardous would be okay. Dyes, sure. Yeast is not an issue either. So I don't know what would be. I don't know how to quantify what is less hazardous or dangerous. I would say they are all fine.
Yeah, and my last presentation will also give you some overview of studies that has been done on tracer, most particularly dye tracer. There are more questions coming in, but I propose that you ask them directly to Luka. afterwards.
I
Otherwise,
will
we
answer
will.
very quickly. There's no problem with it. There's not going to be a problem with picking up with flow cytometry, and will not be a problem in terms of particle counters. So absorption of dyes by yeast is not a problem.
Okay. Well, we'll stop here with the questions and go to the second presentation of my colleague. Thank you, Luka.
Yes, thank you. So we'll share my screen. So can you see the screen with the presentation?
We can see your screen, but just maybe put it in presentation mode so we see the full presentation.
Sure.
Yeah, perfect. Thank you.
Good morning, everyone. So I'm Amaël Poulain from TRAQUA. I'm a hydrogeologist, and today I would like to talk about some optimization we did recently together with AGT, Advanced Groundwater Technique, and IFTEC in Belgium, optimization of dye tracing with fluorescent dye to characterize ATES geothermal system. So I want to thank the team of AGT, which is also in this webinar for supporting us for this optimization. So what is the context of ATES? Basically, this is an open loop geothermal technology that is used as a energy storage in groundwater, and it is based on 2 or more wells that you drill in a productive aquifer, and you use those wells to pump and inject water as if you need to pump or inject according the season. And it is useful because it is used both for heating and for cooling according to season, according if you want to cool your building or warm your building using your energy storage. And so the implementation of ATES is growing, especially in Europe, due to the energy and climate policy, and also since it is a sustainable energy which is using local resource, meaning the groundwater. And it is more often used in large buildings like office, hospital, airports, and more often also used in cities. And in cities, the footprint of project is obviously reduced, and so the proximity and the possible interaction between projects using the same aquifer for this energy storage is quite obvious. So let's talk a bit about thermal recycling and the system performance. In such a geothermal loop, there is a possible thermal recycling, which is the interaction between your wells, meaning the warm and the cold wells of your system. And this might lead to a decrease of the efficiency and the performance of your geothermal system. If you have a bubble of cold or hot water reaching your having connection between your wells. And so this thermal recycling obviously relies on different factors. The proximity of the wells is one of those factors, and also the hydraulic gradients in your in the aquifer in a local or regional situation, the type of aquifer, porous aquifer, fracturated aquifer, the flow velocity in this aquifer, and also the possible existence of high permeability pathway that will enhance the velocity of groundwater in your aquifer. Also, the existence of multiple projects in a very small area using the same aquifer might lead to thermal interaction between different aquifer, between different projects. And so you must know this potential thermal recycling to properly adjust your system, and also to evaluate the performance, meaning the heating or cooling capacity of your system. There is a lot of techniques to assess the performance of your system. A lot of tests, obviously pumping, injection tests that are used and needed to evaluate the aquifer response to when you pump or inject water in a quantitative point of view. You have groundwater models that are used for prospective analysis to evaluate how it will go into the future. And heat transfer tests, which is common, use it to know the thermal behavior of your aquifer, but which it is a test that it is quite expensive and obviously takes a lot of resources. Also, the high resolution monitoring of temperature in your loop, which needs a lot of time to evaluate how the system is reacting in a long-term perspective. And last but not least, the dye tracing using dyes and fluorescent dyes especially. Let's see how it can be useful in this situation. The dye tracing a geothermal system is not new. Actually, to characterize connectivity between different wells, it is used since the 80s. You have several experiments in Iceland, United States, France, in a very large geothermal system. But mainly, this is tracing on big experimental system with deep wells, large quantity of dyes, very long time of restitution. You have an example from on the right experiment in the United States using fluorescent dyes. You see that we have restitution for days and days and sometimes for years. This is more often high temperature system, and the measurement is made by sampling and analysis, since there was no need for high temporal restitution resolution in this situation. So manual sampling and analysis in the lab was sufficient to provide good data for those dye tracing. But what about this, let's say, smaller and more domestic system? For example, in Belgium, with lower temperature, lower depth, sorry. And I will show you two examples of the ETS potential in Belgium. We have in Brussels, in the Paleozoic bedrock, which is fracturated quartzite and phyllite, which is a very productive fracturated aquifer, actually. But in this city, the wells are often very close because the footprint of the project is in city reduced. And so the question was, what about the thermal recycling due to the fracturated aquifer where it's implemented, where are implemented wells? On the left, you have a cross-section, typical cross-section of the geology in Brussels with the Paleozoic basement on the basement, and above you have the different sediments, more recent sediments in this region. So the evaluation of the thermal recycling was an opportunity to use fluorescent dye tracing. The challenge were that we need a high temporal resolution for dye monitoring because we have potentially a short restitution times within a few hours or within a few days, because of those systems are quite small in terms of spatial position of the wells. The dye tracing is implemented during the classical pumping injection test to test the wells in a quantitative way. So this is a closed system, a pressurized loop, and it is not possible to deviate or to sample the groundwater in those in this loop, because the system must remain closed because it is under pressure. Also, to ensure the stable operation of the injection test, to have a stable discharge, pumping and discharging your test, you need to remain the system under the same pressure. And also there is no authorization. It depends on this project, but there is no authorization for groundwater abstraction and a surface discharge of water. So you cannot divert or deviate your system with a faucet because you cannot sample the water in a continuous way. What about manual sampling with a faucet, like we saw on the historical dye tracing and geothermal system? Obviously, there is a lot of workforce needed, so it will cost much money for manual operation. When you sample, the pressure is temporarily lowered, so there is discharge variation in the system, which is not very damageable for the preparation, but still it is a perturbation of your test. And also we saw that there is a turbidity variation due to the discharge variation, due to the modification of the pump regime. And so this might lead to perturbation of the optical measurement of the dye, especially if it is measured with optical system, in situ optical systems. So to address those challenges, we did an optimization in at least for now 2 study cases in Brussels together with the company AGT and IFTech. The idea was to have a closed injection loop, pumping and injection loop, which is under pressure with a distant control of discharge and pressure. This is the basis, the basic situation where we implement the dye tracing. We design a reusable bypass in the loop. You may see the bypass here on the left side of on the picture on the left side. So this was made for a pressurized measurement of the dye in the loop, and we design reusable flow cell to use our stream fluorometer to measure continuously the dye in the loop. So stream fluorometer is able to measure up to 3 different dyes, fluorescent dyes, continuously with a high resolution time step. So they are implemented here in flow cells. And by doing so, we have an automatic and high temporal resolution of different multiple fluorescent dye in the loop with a limited workforce and maintenance. And next to this measurement, we have an under pressure injection of the fluorescent dye here in the injection well. And so we designed this instantaneous and controlled injection of the dye, also to avoid the perturbation of the system and the pressure during the injection test. The advantage was that when you inject your dye, your system is on since a few hours or a few days, or the system is stable in terms of flow rate, in terms of pressure. So you are in a steady state in a hydrogeological point of view, which is you want to have if you want to model your system in the next step. The dye monitoring is continuous. There is no sampling, so there is no perturbation in the loop in terms of discharge, turbidity, and you get a higher stability of the measurement of your dye and of your general operation. Some view on the results. This is 2 recent examples we did in the Paleozoic basement of Brussels. First, so we had a next to the results itself, where we had a very quick restitution of dyes in both situations in a few hours, with very high velocity of dye in the system, in the fracturated basement. So potential very high thermal recycling in the system for a given discharge in the system. We can see that the breakthrough curve are not noisy, which is often the case in such a dye tracing operation because the system is not steady. But here, since you have a very steady state system, it is easier to get a nice breakthrough curve, which is easier to use in hydrogeological model. You have no perturbation of your breakthrough curve. It is so easy to evaluate the timing, the first arrival here, the model time, the total restitution time, so the flow velocity that you will calculate for a given discharge, a given distance between your well. You may calculate the recovery rate because you exactly know the discharge of your test. And the idea is to evaluate the potential thermal recycling into your system. If you have a very, very high recovery rate, then it means that your dye and your water that you inject in your injection well is totally recovered in your pumping well, which is obviously not good for the optimization of your system and the performance, potential performance of your system. And another interesting result is that the multiple you may perform multiple experiments easier because once your system is set with the bypass, with the flow cell and the fluorometer, you may repeat the operation with different discharge, different injection sites or pumping wells, depending on your system. You may have different injection wells that you want to test, different pumping well that you want to test, or also different tracer. Why not yeast in this case? And obviously here we use fluorometers, so this system might use different dyes, fluorescent dyes, sodium fluorescein, different kind of rhodamines, and also ultraviolet tracers, for example, to test different configurations. So, in conclusions, this was a very short overview of what we have done in the recent months. But I would say that the ETS market is expected to grow, especially in Europe in the future, and also especially in cities, because that's where you have big buildings, big infrastructures that where you may implement ETS as a heating or cooling system. And in cities, space is limited, so the thermal recycling of the geothermal loop is possible. It depends on the context. It's not always the case. It depends on the type of aquifer and on the utilization of the system. What is the value of the discharge you want to operate the system? Obviously, it is especially possible in fracturated aquifer, where fracture will concentrate a lot of your aquifer productivity and most of the flow in your aquifer. In those systems, there is also possible interaction between neighboring projects. This is possible. This is not what we tested here, but obviously it's something that can be done. And dye tracing offers a simple and, let's say, cost-effective way to characterize geothermal loops next to classical tests, next to groundwater modeling, and next, for example, to heat tracer test. Here we have a system that we design together with TRAQUA and AGT, and this offers the opportunity to acquire without valuable data about how your aquifer it behaves and how we can optimize the system in the next step. So thank you for your attention, and I'll answering. If you have any questions, please ask.
Thanks, Amaël. I don't see questions coming up. Just Luka is
Thank you, Luka.
saying excellent talk. I think Lorraine has a question. Don't hesitate to just ask directly open the mic and
Yeah, hello, Amaël, thank you. I wondered, what was your conclusion of this study? So apart from the quick first arrival, what else could you deduce from this tracer test? I was wondering about the strong retard effect you observed on your curve. Have you conclude anything about that, or the main conclusion was only the first the quick first arrival?
Thank you for the question, Lorraine. Actually, the interpretation of those data is still ongoing. We work together with the engineer of AGT, so I will not. I don't have any answer about that. But on the first view of those data, of course, the time of arrival was the most significant result we can interpret. Why? Because since you have a recycling of water, you have also recycling of your dye in the system. That's something we still need to study. What is the actual recycling of the dye that can lead to restitution rate more than 100%? Because if your recycling is very quick, then the kilo of tracer you inject will flow into your measurement cell again and again and again. Of course, at a certain point is diluted by the aquifer, and that's why we have decreased. But I would not interpret too much the retardation effect we saw and the tailing of the curve, because obviously it's also due to the fact that you recycle the dye into the system. So for me, the most interesting information that we can use in groundwater models is the first arrival, the peak, and then see how the restitution rate is rising with time, and is it informative or not on the do we have more than 100%? Do we have 10%? This is an information for me very useful to inform about the effect of the recycling.
Okay, thank you.
First, I will go with a question of Neda, David. She asks, do you know what the law says about ATES systems? Because the temperature of the water changes when it returns to the underground. Do you have some information about the law?
No, to be honest, I don't know exactly what say the law, especially in Belgium, when we have a lot of different law according where you put those system. Maybe our friend from AGT might answer those questions, but I don't want to.
Yeah, if you want.
Yeah.
So the minimum temperature that you can inject is 4 degrees, and then maximum is 25 degrees. So these are the limits.
And is this for Belgium, or
this is
this
for
a European?
Brussels and Flanders. I'm not sure about Walloon, the Walloon region. Yeah, and maybe I wanted to add, Amaël, to your conclusion about the recycling, that indeed we are focusing in our modeling on the arrival of the peak, and from that, for now, what we have is a better calibration on the porosity of our model and the thickness of our permeable layer. So yeah, but like you said, indeed, there is an important recycling because we pump around the dye again and again.
Thank you, Annabelle. Yeah. There is one more question from Tom Thompson. Could this ATES system be adapted to off-grid use by self-builders, or is it too technologically challenging?
I'm not an expert, but I would say that given the important investment that it represents, it is obviously more adapted to a large project with a lot of volume to eat or to cool. So I don't know what Tom said by self-builders, but for the case of houses, the closed geothermal system with probes is, I think, more often used in Belgium, actually. So not open loop system with exchange with the aquifer.
Yeah, I hope that answered your question, Tom. So if there are no more questions, I think we can go to the next presentation of Elke.
Thank you.
Thank you, Amaël. And of course, if there are more questions afterwards, don't hesitate to
Please,
contact us.
All right. Can you hear me?
Yes, we can hear you.
Okay, great. And let me share my presentation. Okay. Can you see the presentation full screen? All right, cool. So hello, everybody. My name is Elke Mugova. I worked on the presentation together with my colleague Christian Wolkersdorfer. And we are working here together in South Africa at the South African Research Chair for Acid Mine Drainage Treatment. And we will talk about tracer tests in flooded mines, a bit of a special field in tracer tests. And in our case, I would like to give you an example from the Havelock Asbestos mine in 𝗦𝗽𝗲𝗍, Swaziland, here in Southern Africa. So maybe let's start first. Why do we conduct tracer tests in mine water? Because I guess not everybody of you is familiar with mine water. So let's come to this. So like Amaël just said, we also want to investigate if there might be a contamination of groundwater by mine water. We need to conduct tracer tests to check the location, but also the reliability of dams. And now I'm specifically speaking of dams in flooded mines or like in partially flooded mines. So sometimes you have a mine with shafts and horizontal galleries or levels, and one part of the mine is separated from the flooded part, and then you need to check if the dam is still reliable or if there is some seepage coming through the dam from the flooded part of the mine to the unflooded part of the mine. Then in general, with tracer tests, we can investigate the flooding process after mine closure, so how the water is rising inside the abandoned mine. We can prove the water flow within the mine. So where is the water flowing? Is it coming out at location ABC? And as well, the duration of mine water treatment facilities. It's like sewage treatment facilities just for mine water. And obviously it works a little bit different, but it's the same principle. And then we can also investigate mass transport. So the first picture is just one of adding uranium into a flowing stream. But in our case, that could be a mine water, mining influenced water. And here's a tracer test that we conducted in a settlement pond from a former coal mine in Germany. And usually the water should flow through the lamellas that are in the settlement pond so that it has a long residence time. But with the tracer test, you can nicely see that the water took a shortcut. So we could prove that, or we could prove why the water treatment system, the settlement pond, is not working properly, why it's not reaching the iron values it should reach, because the water is taking a shortcut and is not flowing through the entire settlement pond. But now let's come to Bulembu. So this is a map of South Africa, and probably all of you know where South Africa is, but have you heard of Swaziland? Now it's called 𝗦𝗽𝗲𝗍. That's a small little country on the eastern side of South Africa. It's about 4 to 5 hours drive from Pretoria or Johannesburg. And here you can see it. To zoom in a little bit closer, the Kruger National Park is up here. And Esprit is a closer town, and Barberton is a former, actually there's still mining, but not to the extent it was there. So there's a mining town, Barberton. And if you drive into the mountains and over the pass, just behind the border between South Africa, there is Bulembu, a former mining town. I will tell you the history just now. And this is what you see when you drive into Bulembu. So my colleague Chris Wolkerstorfer, he was driving around in Eswatini for vacation a few years ago, and then he came to this town and thought, that's a mining heap. What is this doing here? But there were no like remains of mining except the heap that you could see from the street side. But then he was driving around and he was investigating that place, and overall, it seems there was very, very big mining activities. You can see there's a really huge waste rock pile or tailings dam. This is the small town of Bulembu, so it was a mining town. And after a while, he figured out there was the fifth biggest or one of the biggest asbestos mines in the world, and it caught Christian's interest, and he started to do a hydrogeological baseline study here in Bulembu. So a short history about the Havelock asbestos mine. This was one of the names of the mine, but the one that we are using now. So it's in the northwestern part of Eswatini, about 20 kilometers southeast of Barberton in South Africa. And it's about 4 kilometers south of Eswatini's highest peak, the Mlembe, which is 1,862 meters high, so really in the mountains. Surrounding rock is quartzite, granite, biotite, muscovite schist, and serpentinite, these names. And the last one is containing the asbestos minerals. And if you walk around there, you can really see it. You can hold the asbestos or the serpentinite in your hands, and you can really nicely see the asbestos fibers. The open pit in the underground area was 1.5 by 0.4 kilometers, and the overburden and tailings is about 50 hectares. And chrysotile or the asbestos mining began in 1939 and ended about 20 years ago in 2000. And until 1980, the British company Turner and Newell was conducting the mining. Then it was overtaken by state. And you maybe heard a little bit about asbestos mining. A lot of how should I say this, questionable things happen there. So it's good to educate people about the asbestos mining and what happened there, but that's not the topic of today. You can read our paper about it. Today we want to talk about mine water. And yeah, just the last factor, asbestos production between 1939 and 2000 was 1.8 million tons, and it was one of the 5 largest asbestos mines in the world at that time. You can just see, to get an impression, a picture of the miner underground. Water is flowing out here. The miner is holding a sign, danger. And yeah, that was inside the mine. Another impression you get here is, I think it's from the 1980s. This is the shaft I will talk about later because we injected a tracer there, so just have this in mind. This is the head frame of the main shaft. There were 3 or 4 shafts in total there. And then this is the production facility. And now if you would stand up here and look into the valley, you would see the former open pit mine. You can still, when you're there now, see it somehow, but obviously it's now all overgrown by forest. Now, to trace the tests in Bulembu, this is not Bulembu, this is just me trying to be a little bit creative, but I think it gives you a good impression of where we investigate mine water and where are our sampling or our testing locations. So in Bulembu, we did tracer tests on the surface waters, and in our case we conducted flow measurement and used the salt tracer, and then with the salt dilution method, and then we also conducted tracer tests in the underground mine, in the flooded underground mine, with sodium chloride and uranium. So flow measurement with tracer. It's a very interesting method, the salt dilution method with sodium chloride. So it's just normal table salt that we get from the shops. It's also called the sudden injection gulp method because you suddenly inject the tracer solution, the brine, into the water. And it's used if there is no even riverbed, if the water level is too low, or if there is turbulent flow, which you have quite often in mining influenced water. A little scheme how it looks, but in the next picture I will explain this in more detail. So just that you have an idea, we inject the salt and then we measure over a distance how the salt concentration changes. And our team uses the set TQ tracer from Sommermesstechnik GmbH. It's a company from Austria, and it's an automatic system. And this is how we install our probes. We have 2 probes, but you can also do it only with 1. But just for you to know, you don't have to use the TQ tracer set. It's a very convenient way because you can do 1 measurement in about 20 to 30 minutes. But you also just can record the electrical conductivity over time and write it down manually. And then you have to use an Excel spreadsheet for the calculations. So just let me introduce to you how this measurement method works, because it's a tracer test, but we use it not as you maybe usually use the tracer tests. So what you do first is you have to collect water samples for calibration, because we measure the electrical conductivity, how the electrical conductivity in the water is changing. But because the electrical conductivity is proportional to the salt concentration, that works out. So we first have to calibrate. Then we need to position our probes, or 1 probe, 2 probes inside the stream, usually in the middle, or 1/3 from the side if you use 2 probes, and 30% over the riverbed. And we have to produce a tracer solution. We have to produce a brine. So what do? We just take water from the stream and we mix it with table salt. And the amount of tracer, how much salt we use, we estimate from the flow that we estimate before. So you probably know after time you see the river and you can somehow say, okay, that's 10 milliliter, that's 10 liter per second, or that's 100 liter per second. And then from our estimation, we calculate how much salt we use. And the distance we have to have between point A, where the injection site is, and point B, where the measuring site is, it's about 25 to 50 times the width of the stream. So we produce the tracer solution, then we have to start recording, because we need the background concentration, obviously, before the tracer concentration peaks. And then we injecting the tracer solution into the stream, and that's also the name sudden injection gulp method, because needs to be injected quickly. And then after recording the peak, we can stop the easy recording when the tracer concentration, when the salt concentration, when the electrical conductivity in the stream is more or less back to background values. So how does it work? With the salt dilution method, we use the integral under the curve. And with TQ tracer, we get instant results of the velocity in liters per second. And you can see the curves, you can see them live, how they develop. So when the curves are going back to background value, we usually stop, and then the software immediately shows us the results. It is very recommendable with this measurement, but in general flow measurements, that you repeat in different seasons and under different weather conditions, because here in South Africa we have also in Eswatini, we have a dry season in winter and we have a lot of precipitation in summer. So repeat measurements are really recommended. Now we did this in Bulembu at different locations, especially at the streams and at the Havelock mine discharge. So at the point where the water is flowing out at the mine, and as you can see here, we were around 56, 59 liter per second. And then here at the two rivers, we were at 79 to 57. That was a bit more upstream. The 57 is in wintertime. And then to Tutsi River downstream, the flow increased because, yeah, there was more inflow into the river, and we measured a higher discharge. And this method works really, really well. It's not known everywhere in the world. We only introduced it in South Africa about 12 years ago to the Geological Survey. And it works very well for mine water, and it only has a 5% error range. So it's really reliable with the conditions that I mentioned before. But now let's come to underground tracer tests in Bulembu. So our first tracer test that we conducted there, it was more actually because it was the first time we came there and we didn't bring fluorescent dye. So we just used the salt dilution method again, similar like with the streams, and we injected the brine into a flooded shaft. So here you see a cross section of the main shaft. Remember, I showed you that picture of the head frame, and this is where the shaft is located. So here's the shaft, and then the shaft is flooded until level 555. And we injected the tracer, the sodium chloride, the brine, into the shaft, just with a bucket, injected it. And we used 2 kilogram salt in 20 liters of water. And then the brine, so the idea would flow through the mine and through the mine voids. I don't have a detailed cross-section now here, but just imagine a lot of mine voids there, galleries, but also broken down areas. And then there's the discharge point here where the water is flowing naturally out of the mine. So there is no pumping. The water is just flowing out. And we recorded the electrical conductivity in an interval of 20 minutes with a Van Essen CTD diver. So our results, could we see an increase of electrical conductivity at the outflow? No, we could not. And what happened? So probably the density of the tracer of the brine was too high and it sank into the shaft sump. And furthermore, the sampling time was too short. We had to leave again and we only had 4 days to measure. So yeah, these two factors probably play a role that we didn't find anything. And you might think the tracer concentration was too low, but this is our experience with mines, and it works quite well. So the amount of tracer was not too low, but probably the sampling time was too short, so we could not detect any tracer. But we came back to Bulembu a few months later, and then we used fluorescent dye, uranium, also injecting it into the shaft like the sodium chloride. And this is how it looked. So this is the concrete slab that is covering the former shaft. The head frame was up here. And we injected 500 gram uranium in water. And this is how you can see here how my colleagues injected the tracer. So there was a borehole available that you could access the shaft, and then the colleagues just injected the tracer. And here another picture which just looks nice, and you get a feeling how we inject tracer into flooded shafts. So we measured again the tracer concentration at the outflow, and this time we used a fluorimeter, the GGUN FL30 from Switzerland. It's a flow with a flow-through cell. We connect some hoses, and then the water, the outflow is just flowing through the flow cell. But we also used the stream probe from TRAQUA just to have both and to compare them with each other. And also for your information, we had an expected underground pathway of 1.4 kilometers. So usually the water is going down and then it flows up and then it flows down again. So it's not just a straight way because the actual distance is just 1.1 kilometers between the shaft and the outflow, but the actual distance in the mine is longer. So these are our results, in this case with the GGUN from Switzerland, but the TRAQUA probe showed similar results, and you can see 2 peaks, and the first tracer arrived already after 1.5 days, we had a peak after 4 days and a very low mean residence time of just approximately 8 days, which is very low for mine water, which tells us that the mine pool is well mixed. The water is flowing quite quickly. And the tracer test could explain the relatively low mineralization compared to water draining through the Bulembu waste rock pile. So there we have a high mineralization, so to say bad mine water. But at the outflow of the asbestos mine, the mine water quality is relatively good. But you also have to consider the mine was already closed 20 years ago, and the mine water quality is usually improving over time. It also explains the similar water quality at the drainage edit, so where we measured at the outflow, but also at the inclined shaft. So we were able during our investigation to go inside the mine and measure water quality inside the mine, and it had also good quality. So there is really good well mixing in the mine. The second peak that you could see in the curve is probably because the water flows through or percolates through broken rocks. So there is no direct connection anymore between the shaft and the outflow, and it just percolates through. So you have some retention there. But at the moment, we can't prove this. And this is just a picture to show you how it looks inside the mine. This is this relatively blue mine water there, or it appears blue. And yes, it's very excited to go into an old asbestos mine that was closed 20 years ago. Now we did something unique there in Bulembu that hasn't been done in mines so often before, and especially not in flooded underground mines with tracer tests. We were able to do a depth logging with the stream fluorimeter at the Havelock vertical shaft, so at this main shaft, and we were recording the uranine concentration over depth. So we used the TRAQUA stream probe, and we attached the probe to this winch. You can see the winch here. It's just a regular winch which works with a battery. And this is only the cable while we were reading out the probe with the computer, but usually you just hook on the probe to the winch and then you can lower it down autonomously. And here you can see how we lower down the probe into the flooded shaft. So what we see here, this is the temperature over depth. And this is quite typical for mine water, that the depth is increasing, that the temperature is increasing over depth. But in this shaft, at least in the area where we measured, we did not find stratification. I will talk about stratification on the last slide, but this is just a mine water body with increasing temperature. And then the orange line is the uranine concentration over depth. And you see there is tracer distributed over the entire measured water body, and it's increasing with depth. Of course, we added it at the surface, and then the tracer is sinking down. But if there would be convection cells, and this is our first interpretation, if there would be convection cells, the tracer would be distributed much more evenly, but because there is no stratification and no convection cells, we have this relatively uneven distribution of the tracer. And it's also to mention that we were not able to record over the entire shaft depth because we could not lower down the probe any further because the shaft is blocked, although it goes down much deeper. So a short summary for you. The tracer tests in Bulembu really helped to understand the hydrogeological situation at a flooded mine. And the more we understand situations at flooded mines, the more we can transfer or apply our knowledge to other mines that are still in the flooding process. So every mine that we investigate is really, really relevant. So we understood more or less the hydrogeological situation there, and we can transfer our knowledge to other mines. We were able to explain the good mine water quality due to the low mean residence time and the good mixing. And we saw again that tracer tests are a really suitable tool for investigating flooded underground mines. and we can inject the tracer either at the water surface, what we did in this case at the Bulembu mine, but our research group also has a device where we can release the tracer at a certain depth. So we can lower down the device and we can say, okay, let's say 200 meters below the water surface, we can open the device and release the tracer there. And then we can even work with different tracers, let's say uranine and eosine Y, and release them at different depths. And for future, we did this already at 2 mines in Germany, but I think it's a very promising approach, is to conduct tracer depth profile measurements in flooded shafts and to detect the density stratification between different water bodies. And this is, just the last thing I would like to talk about, which is not so much tracer relevant, but tracer tests help us to investigate stratification, because almost every flooded underground mine, and we investigated over 60 mines worldwide, is stratified. So you have a lower water body, it's called a warm mineralized water body with relatively bad water quality, and you have an upper water body, it's called the cold fresh water body. And if the water is stratified between these two water bodies, or can be even more, you have relatively good quality on the surface, and the stratification acts like a barrier function. And we can prove this barrier function with the tracer tests, because if we conduct a depth profile measurement and we see all the tracer is stuck down here, then we have a proof that the barrier function of the tracer, that the barrier function of the stratification is really working. So a little bit more about expertise in mine water tracer tests. As I said, I'm currently, until end of the year, I'm working at the South African Research Chair for Mine Water Management, together with Professor Christian Volkersdorfer. And he usually gives once or twice a year a 1 to 2 day short course about hydrogeological tracer techniques. And this short course is specifically about mine water, if you conduct tracer tests in mine water, because mines behave differently to caves, for example, and you really need to understand the hydrogeological settings in mines. And if you're interested in consulting work, so if you need us to conduct a tracer test for you, now in this case in a flooded underground mine, you can check our website. Thank you so much.
Thank you.
Thank you, Elke. Very interesting. Are there any questions? I saw already a remark from Tom Thompson. He said that it's really interesting because they also use salt gulp to measure input volume to a cave system and then the output. And it was very interesting to see this used with modern equipment.
Yes, thank you. Yeah. So this TQ tracer set, I'm not paid by the company. Don't get me wrong, but it works just really, really well, and you're very effective if you have to measure at a stream at different locations, because within the day you can measure 4, 5, 6 locations, and you really get a reliable flow measurement.
Okay. Any other questions or remarks? I think I'm sure they can always contact you with further questions about mine tracing.
Yes, I will post my email address in the chat, and then you just can get in touch with me.
Okay, perfect.
Okay.
Thank you, Elke.
Thank you so much.
Okay, so now we will move to the next speaker, which is myself. Don't worry about the time, it will be a lot shorter because I'm not actually giving a presentation. I just want to share you some resources that we have gathered. I will share my screen. Let's see. Yeah, here we go. So last year, I conducted with 2 internship students from university, no, not university, the Polytech Montpellier, so Rudy and Jeremy. We have conducted some kind of article overview on topics related to fluorescent dye tracer tests, so which was toxicology, but also regulations in Europe. So We looked at what was available in terms of regulations in European countries, and also we looked at what was available on research that had been done in the past on toxicology of fluorescent tracers. They wrote some kind of book, like a report about it. I then summarized it into a poster that was presented at Karst earlier this year, just to give you a short overview of articles and information that is out there available. Just to give you some idea why did we conduct this? Of course, first of all, it's interesting for ourselves because we sometimes conduct tracer tests abroad, so it's always good to know what regulations are in other countries, also what tracers are best to use and which ones are better to avoid. But we also wanted to provide this overview, well, in this case, a poster, to other institutes or research institutes that want to perform tracer tests, but are sometimes blocked by their regional authority. And the reasons why they are blocked are not always clear, but most often it's because it's not very commonly known. Sometimes the local authority are a bit afraid. They see this fluorescent dye, they don't know what it is, so they don't give permission to provide tracer tests. So we hope with providing this information, easily accessible information with a lot of, you will see later down at the poster, there's a lot of references. We hope that this overview can provide some additional information if you want to apply for example, a permit to perform a tracer test. So this is what we did with the students. We read a lot of papers that discuss the topic of toxicology of tracer tests, and we summarized it into this overview. Of course, the assessment is quite general. They just mention safe or some concern or unsafe. They don't always give exact concentrations. There's only one paper that I know of, written by Carrier et al. In 2007, that mentioned a specific concentration of 2 milligrams per liter that poses no risk for any of the traces mentioned here. But in general, they just mention safe, some concern, unsafe, etc. This table that you see here was based on the research done by Behrens et al. And then with the little numbers, there are some updates of more recent papers. Another thing that I want to point out, of course, Carrier et al. Mentions some concentrations. This is why it is also very important when you conduct a tracer test to really analyze the hydrogeological conditions beforehand, to do a good literature study, some field study before conducting a tracer test, so you can choose the good concentration that you're going to use for your injection. Then the regulations, I will give you another overview with a little bit more detail, but of course, we looked at all the European countries for now. Maybe in the future, I will look to other continents, but for now, we started with Europe, but this was already complicated enough. And we also provide resources on tracer test design. So these are a lot of papers that are available that discuss how they perform tracer tests. There are some guidelines available as well. So I will share this. This is available online. I will share this poster. You can click on the links and have a look at all the resources that are available yourself. So now in terms of regulation, so I will take this same map here again. So how did we go about? First of all, me and my 2 interns, we started off with some previous research that was already conducted by Professor 𝗦𝗲𝗿𝗀𝗲, so the same professor that is the colleague of Elke, because he already conducted some research on regulations specifically for Canada, but he also mentioned quite some European countries. So we took his research as a basic to start off our research. Of course, he didn't focus on Europe, so we added quite some information on countries that were not in his list, and we also updated because his research dated from 2012, which is already now 12 years ago, so we did some updates. How did we update this? So we contacted National Geological Surveys, but also experts locally that conduct trace tests in their country, and ask for confirmations on our assessments. So as you can see on the map, some countries require authorization. Some countries have guidelines, so these are the ones with the stripes. Some countries don't mention any requirements for authorization, although it is in general highly recommended to inform your local authority, and also if you do it in an urban location, also to inform, of course, the local inhabitants, because if there is a visible tracer, they will of course be frightened, and they might contact the police or and of course we want to avoid this. Some countries I don't have information yet, so if you happen to be of one of these countries, please contact me. I'm always open for new information, updated information, because this is not a fixed document. This is a document that is open to updates and to new information all the time. So this document for each European country, I reuse the structure of Professor Wolkerstorfer for this table. So each country has some indication if there's a guideline available, if there's really a fixed legislation, if there's a requirement for authorization, and so on, where you can find this information, or if there's some local recommendations or guidelines available, and with a clickable link on where you can find this information. So this is a whole list of European countries, plus, of course, including also the United Kingdom and Switzerland. Just two countries that I just want to point out are Slovenia, who did a really wonderful job in creating a GIST database with all the previous tracer tests that have been conducted. It's quite impressive work because they conduct a lot of tracer tests in Slovenia. That is a country very rich in karst. And also Switzerland, which has a platform which is called InfoTracer, that's on which you have to indicate if you're going to perform a tracer test. And of course also has a history of the previous tracer tests, which is very practical because then you can avoid performing two tracer tests in the same area and have potential interference. So I think this is very beautiful work that has been conducted in these two countries. And of course, yeah, there's other information. If you have updates, if you say, hi, I'm from this or this country, and I know there's some regulation about tracer testing, don't hesitate to contact me. My contact email address is also in the document. And this document is also available online, and I will send you the link to both posters via email. So this was my short, not really presentation, but just provide you some resources that might be interesting. Now for a final surprise announcement. TRAQUA in collaboration with Luka from Glasgow Caledonian University are planning to organize summer training next summer, so by the end of August, on tracer testing. Not on mines, more on environmental, like surface and groundwater, for example, caves, what we are specialized in. So this is not fixed yet. It's an idea that we are developing. But if you are interested, don't hesitate to contact either me or Luka. It's planned to be a live course, so a 2 days event in London at the Glasgow Caledonian University, with 1 day more theoretical about tracer testing in general, and then a second day with including a field trip where we actually perform a tracer test and then in the afternoon analyze some data. So yeah, if you have questions about that, don't hesitate to reach out to us. We are still in the development phase of this course, and we are trying to have an idea about the interest for such a course. We also thinking about providing the first day, which is more the theoretical part, to make this available online so people can subscribe and don't have to come to London. But the idea would really be to provide also some field training. So that was it for me. I don't know if there are any more questions, either for me or for one of the other speakers. No, they don't seem to be questions. I saw that Elke also posted her contact information in the chat. So if you want to contact her, don't hesitate to reach out. So if these are no other remarks, then I think we finished this webinar perfectly on time. And the recordings will be available soon, and you will get the link to the recordings, as well as the links to the two resources that I just presented. I will send them to you via email. So thank you very much. Thank you for being here, and have a good lunch.
Thank you, Sophie. Thank you, everyone. Bye.
Thank you all.
Bye.
Bye. Bye.